A lasting structure begins not with concrete, but by controlling where the water goes. Before any weight is added to this site, the builder must define the drainage footprint. Trenching through compacted gravel sets the baseline for everything that follows. After leveling and tamping the base layer, the underground utility network takes shape. Orange PVC piping forms the primary drainage arteries for the foundation. Using a specialized lubricant ensures the fittings slide together fully, preventing bound joints before the chemical weld can set. The branching pattern is calculated to intercept and channel moisture away from the future slab. Water is a foundation's most persistent enemy. If trapped beneath the concrete, freeze-thaw cycles can crack a solid slab in a single winter. By establishing a central hub and connecting individual branches, the builder creates a gravity-fed evacuation route. The entire system rests on a carefully graded sand bed, which provides uniform support. Hard rock or uneven soil could create pressure points, eventually fracturing the plastic under the immense weight of the finished building. Once assembled, this network will disappear entirely, silently protecting the structure above. Backfilling with pure sand locks the pipes in place without introducing sharp rocks that could puncture the line. But burying the system is only half the job. Before locking this layout under tons of wet concrete, the builder performs a simple gravity test. Pouring water directly into the openings verifies the slope is correct and the joints are perfectly sealed. Finding a leak now costs a few minutes of digging. Finding one after the pour is a structural disaster. With the plumbing buried, the thermal barrier begins. A hot wire cutter slices through the extruded polystyrene insulation, melting the material rather than tearing it. This leaves perfectly square edges. Dense foam boards like these prevent the earth from wicking heat away from the finished floor. The tighter the cuts, the better the thermal seal. Working across the newly laid sand bed, the builder custom fits panels around the protruding drainage pipes. Even a millimeter of space around these utility penetrations represents a thermal bridge where cold can enter and heat can escape. Expanding polyurethane foam solves this. It chemically cures as it interacts with moisture in the air, swelling to fill every microscopic void between the plastic pipe and the rigid insulation. Once cured, the excess is simply trimmed flush. This meticulous sealing process ensures the foundation behaves as a continuous, unbroken envelope against the elements. It takes time, but this invisible prep work defines the future energy efficiency of the structure. After drilling the base panels, the perimeter forms a rigid tray. Mechanical fasteners lock the final insulation layers directly into the base structure. The interlocking edges of the panels prevent shifting during the high-stress concrete pour. Building is often a generational transfer of knowledge, and here, an extra pair of hands helps align the massive sheets. Driving the long fasteners requires keeping the drill perfectly plumb, ensuring the structural anchors bite straight into the sublayer without wandering. The completed white floor isn't just an insulator. It is the structural canvas for the complex mechanical systems that will soon crisscross the site. Every board must lay completely flat. A single raised edge now would create a weak point in the final slab. With the thermal barrier locked down, a hot wire tool carves precision channels directly into the foam. These parallel grooves will house flexible utility lines, keeping them safely below the reinforcement grid. Creating these runs directly in the insulation allows the tubing to sit flush, avoiding any interference with the steel rebar that will follow. The blue and red plastic lines indicate separate mechanical zones, organized strictly by temperature or function. Pressing them firmly into the melted channels ensures they won't float or shift when the liquid concrete eventually floods the site. As the radiant heating loops take their final form, rigid gray conduit is woven into the steel mesh. This creates hollow pathways for future electrical wiring. By running conduit inside the slab, the builder eliminates the need to tear into finished walls later. The pipe must be securely tied to the rebar grid every few feet. Concrete is incredibly dense and heavy. As it pours, its fluid dynamics can easily dislodge loosely secured pipes, pushing them to the surface. Tying everything down creates a monolithic mechanical layer. Steel reinforcement transforms brittle concrete into a structural powerhouse. A wire twisting tool securely binds the rebar junctions directly above the fragile PEX tubing. Concrete handles compressive weight brilliantly, but it lacks tensile strength. This steel mesh absorbs bending and stretching forces that would otherwise crack the foundation. Sparks fly as excess rods are trimmed to fit precisely within the perimeter. Every intersection is checked and tied. A loose grid will fail to distribute loads evenly. Before the heavy pour can begin, the perimeter requires serious reinforcement. A hammer drill bores anchor points into the rigid concrete side panels. Liquid cement exerts massive hydrostatic pressure outward as it fills a space, pushing against the boundaries with thousands of pounds of force. If the formwork fails or bows even a fraction of an inch, the entire slab loses its true edge. These drilled holes allow the builder to insert heavy steel anchors, locking the exterior walls to the internal framing. The boundary must be absolute. With the perimeter staked and braced, the mechanical heart of the floor is assembled. A stainless steel manifold acts as the distribution center for the radiant heating system. It features built-in pressure gauges and delicate flow meters to balance the distribution of hot water. If one loop is longer than another, water will naturally take the path of least resistance, creating cold spots in the house. By routing all the red and blue PEX lines into this single, calibrated hub, the builder can finely tune the flow rate for each independent zone. Secured to a vertical rebar stand, it waits for the final pressure test. The final step before the concrete arrives is pure defense. The builder methodically wraps every exposed pipe penetration with heavy adhesive tape, trimming it flush to create an impenetrable cap. Wet concrete is a relentless slurry. It will find and fill any open vulnerability in the system. A blocked internal drain line embedded in solid rock is nearly impossible to fix. Expanding foam provides a secondary barrier at the base, sealing the gap between the plastic and the insulation floor. Heavy bricks anchor the buoyant plastic assemblies down. The liquid concrete will try to lift and float these hollow pipes as it floods the floor. With a final check of the elevations using a metal level, the grid is locked. Rather than relying on manual tamping, the builder fabricates a custom solution. An electric vibrator motor is bolted and welded onto a rigid metal frame to create a powered screed. The intense high-frequency vibrations will force trapped air bubbles out of the wet concrete, settling the heavy stone aggregate to the bottom, while drawing the smooth cement paste to the surface. As the mixer truck unloads, the site transforms into a frantic race against chemistry. Wet concrete begins curing the moment it is mixed, leaving a narrow window to manipulate thousands of pounds of material. The custom vibratory screed is pulled slowly across the surface, riding the perimeter formwork to establish a perfectly flat grade. Behind the screed, long-handled rakes distribute the heavy aggregate, knocking down high spots and filling in the hollows. The vibration liquefies the mixture temporarily, allowing it to flow completely under and around the dense rebar and PEX tubing grid. Without this vibration, invisible air pockets would remain trapped beneath the steel, creating hidden voids that compromise the structural integrity of the slab. It is a grueling, heavy process that demands constant movement. The crew must maintain a wet edge, ensuring the new material seamlessly blends with the old before any sections begin to set. As they drag the heavy beam across the final stretch, the chaotic grid of pipes and steel is swallowed entirely, replaced by a smooth, monolithic surface. Concrete takes nearly a month to reach full strength, but it hardens enough to walk on in a matter of hours. During this green phase, the builder carefully chips away the overflow around the utility penetrations. The adhesive tape and foam defenses did their job, keeping the internal pipes clear. Removing this excess material now is crucial. Waiting even a day longer would require heavy demolition tools and risk fracturing the surrounding slab. Small taps with a hammer Ensure the assemblies remain plumb as the concrete shrinks slightly during the initial curing phase. By meticulously clearing these points, the raw slab is prepped for the eventual plumbing and electrical tie-ins. As dusk falls, a diamond-tipped grinding disc makes the final pass. This removes the latence, a weak, dusty layer of cement paste that naturally rises to the top during the pour, revealing a dense, durable finish. What began as an empty gravel lot is now a highly engineered thermal mass. It is a foundation that manages water, distributes heat, and anchors the future. The footprint is set, and the real build can begin.